So before I go and really talk about simulations for quantum communication, I would like to motivate why I think we should have better simulation tools for quantum communication systems design. And in a sense, Daniel, you paved a large part of the way for me, but I didn't know that before, that he would do that. Okay. So maybe I somehow want to, yeah. Okay. Oh, yeah. He also spoke about meeting at workshops and other events to discuss these topics. So I would like to point out that the EACN is going to take place in Arizona here. Bulat is our local organizer this year, and it's going to be in November. So please consider joining. And of course, it would be great to have you there as well. So why would we need simulations of quantum systems or quantum communication systems? Well, because we want to build some kind of technology, right? I really like those two talks before me now, because I come from the world of the first talk, of the first speaker. But at some point, I ended up working in Dresden, and close to the 5G lab in Eduard's group. And my life changed. Yeah? I thought, oh, what am I doing, and what are these people doing here? There's a huge gap. Yeah. So this was an engineering chair in the 5G days and later 5G summit. That was an engineering conference, and there was a lot of parallelism between like from math to say applied math, to simulations, concepts, and then even startups that built systems, and big companies that were looking into this venue and thought, oh, this is maybe interesting for us. And I thought it would be great to have something similar for quantum. But then when we want to talk about quantum systems, we have to consider that there is a state of the art. And the state of the art does not like changes. The state of the art feeds people, so feeds families, so feeds big corporations. And if you come with something new, then there will certainly be someone that does not like you. And this person will resist and try to kill your invention. So it's important to understand where are the advantages in quantum technology. That's what I want to spend the first couple of slides with. And I started my research based on two formulas. So the first one is Shannon's formula. Yeah. Oh, okay. Maybe I better do it like this. Yeah. So the first one is Shannon's formula in a version that was provided by Konrad Banaszek, actually. And it has the number of symbols per second in it. Here, this is B, and it has the number of photons per second at the sender, and then the number of noise photons at the receiver, and then you have the loss from the sender to the receiver. And this is about data transmission, yeah, in bits per second, with a slight modification down here. Yeah? This is the quantum part. And then we have another formula. This is the Holevo capacity formula. Yeah, this one has the same parameters here, but then the formula looks a bit different. And this is due to Holevo and then later Giovannetti and collaborators as well. If you want to reach this Holevo capacity, then the underlying assumption is that you have a receiver that can store a large number of incoming signals in a nice quantum memory and then operate on it with some sort of quantum computer and do crazy tricks. This is depicted down here. So this is a joint detection receiver. It stores many incoming photons and then does something on them. And here's the conventional receiver, which takes any incoming signal and makes kind of a decision on it. Yeah? It says, oh, this was a signal, a certain signal. Yeah? So it converts it to classical values. When we want to understand what is the potential of the new technology, then we say, okay, let's just look at the ratio of the Holevo capacity by the Shannon capacity, divided by the Shannon capacity. And then we see that if we have no noise, no thermal noise, and we let the transmittivity, for example, go to 0, then the Holevo capacity wins extremely much over the Holevo capacity. And this is great. This is a super cool quantum advantage. And there's one tiny caveat. The data rate goes to 0 at the same time. And I didn't depict that. This is the part that is so much no fun. So if we want to think of this as technology, then we need a low power sender on at least in terrestrial networks. Distances are typically not high enough to allow any other argument, and we don't want any amplifiers. Optical networks are full of amplifiers, and they are really bad for any argument pro using a quantum joint detection receiver. We also want low noise at the receiver, and as I pointed out, we want to look at low data rate applications. And it is possible to find some. For example, we could think of underwater communication where there is no chance of putting an amplifier, at least none that I would know of. We could think of indoor wireless communication, optical wireless, for example. Indoor is nice because then we don't have thermal noise, or we can at least block large parts of it. And we could think of small robots that have a really stringent power constraint, so they cannot emit a lot of photons per second. Or we could think of satellite network scenarios. This is a joint work with Mark Neitz here with Deutsche Telekom. In this example, we have a constellation of, let's say, 1 million satellites, and 1 million satellites that just, if you want to identify those satellites, if you want to put a license plate on it, you need something like 20 bits. That's not a lot. So if you now have a base station that sees a horizon, satellite coming up on the horizon, and wants to understand which satellite is that in this constellation, then it would try to read the license plate. And that's only a few bits. And the loss can be quite high if the satellite needs to transmit through the atmosphere. And people from Los Alamos laboratory have made an optical beacon signal design for such a situation, and they even demonstrated it experimentally. They calculated that the base station sees 3 photons per second in their application scenario. That's where we got interested and looked into the quantum limits of such a design. So quantum advantage exists, but what about the systems? What about the hardware? So in the case of the joint detection receiver, there was one first proposal by Saikat Guha. This is here on the left-hand side. And that's an interferometric mesh network here consisting of tons of beam splitters and phase shifters. And you have a series of incoming weak pulses. Now they enter the entry ports here of this network. And then you construct the network such that if there's a specific sequence coming in here with specific phase relations between the individual pulses, they interfere constructively, and you have one bright output. And if you have different phase relations at the input, then you see the bright output at another output port. And then you can easily detect this. There are also other proposals, for example, ones that use the non-destructive vacuum or not measurement, or ones that utilize efficient coupling of light into a quantum computer. And then you might ask, well, since the latter two are possibly quite hard to achieve, what can we do with the first piece of technology? You can, for example, use it to distinguish between different hypotheses. If you have a thermal source and it emits to your 8 input ports here, and then you place here single photon detectors, and you want to know whether the detection, the signals that get detected by your single photon detectors here are coming from a situation where you have one thermal source that is emitting to all your input ports here, versus another situation where you have actually 8 independent thermal sources. Then it turns out that there's a huge quantum technology advantage. We computed that last year. So you have basically a very different scaling here of the optimal error exponent in hypothesis testing, E versus E squared. If you use the photonic network here with photon detection versus the standard architectures based on heterodyne or homodyne detection. But if you want to make it a technology, you need very low loss optical networks. You need a few bits of photon counting resolution and very efficient coupling of your actual signal into this device. There's another example, which we also investigated, which will be presented in full detail at the ICC this year, where we considered a bit commitment. Bit commitment has to do with a data-driven economy. Yeah? So when we, the way we work at the moment, we create tons of data, and it would of course be nice if you do, for example, drug discovery to treat cancer, to operate on all data points of all humans on the entire world. You know? But it is not a good idea to share all the data with just one single entity and say, oh yeah, we are sure you will compute only the function values of interest to this one very cool case that we all believe is worth it. No, that person will probably abuse the data and do something else with it or sell it to somewhere else. Yeah? At which point secure function computation comes into play, which solves this problem by allowing you to compute only certain function values on distributed data sets and nothing else, just those function values. And secure function computation can be realized using the so-called bit commitment, which is a primitive, you know, where I'm, as the person committing to a bit, can note down my bit value on this piece of paper, put it in a box, put the box here. I know none of you can touch it, and you know I won't change it until the time has come and it will be revealed. So it's binding, hiding, and it's the foundation, or one foundation for secure function computation. But it is unfortunately known that it cannot be realized in any quantum universe, so to say. And it is unfortunately also known to us that we live in a world that is ultimately ruled by the laws of quantum mechanics. So that tells us that we have a big problem, because we cannot make a bit commitment. Anybody that claims he can make it basically claims something that we know is wrong, and we just have to find the mistake. So maybe it's better to derive bit commitment systems that where we clearly lay out where's the mistake. And we made one proposal for such a system. Here we created some complicated quantum state, this one. And I'm not giving you all the details. Yeah? This will be presented at ICC. But this is a complicated quantum state. It's a mixture of coherent states. Yeah? All these states here are basically laser light. They are super simple, trivial. Everybody can make them. E here is the energy, and B is a phase shift that encodes my committed value. Now I will send them through an optical fiber, so many of those photons will be lost. And then it will be some very weak quantum state. And for any person that receives such a weak quantum state, it will be very difficult to tell the value of B unless I give it to that person. And then the person can make an optimal measurement that will tell them whether I was claiming the correct value. And then we can ask really fundamental questions. Because there's an attack, as I said, on any bit commitment system. The attack is to create a purification of the state. And the nice thing about this design is that now we have a macroscopic state. So it should be pretty hard to make a purification of that state. And it will hopefully lead to some basic research to answer this question and evaluate this proposal. But at the same time, we also have very clear, should I say, so when we want to design such a system, it's relatively simple as soon as we have quantum storage. Then we need a photonic computational model. we need to understand the fundamental limits of mode transformations, because I spoke about optics, basically. So I'm implicitly assuming it's in the telecom band, but maybe somebody just transports like some attacker, some person that wants to change their commitment in a mean way, would just not create this state in optics, but in some cool quantum system, some quantum computing system, then make the purification, then couple out one part of it and send it down this optical link. So we should really know whether that's possible or not, and what are the fundamental limits if you build security systems on such a proposal. And now I hope I basically was confusing enough with all these fundamental questions so that everybody understands that this is not a one single person job. Now I spent a lot of time switching between different domains, and in the end I always thought, oh, hard questions, cannot solve them by myself. I will skip this slide. Yeah, so this in academia, we are following, at least that's my perception, a tradition based on following the example of the guy on the left-hand side. Yeah? He was arrested for defending heliocentrism. The right-hand side guy was part of the first mission to land a person on Moon. Clearly defined goal, executed in 8 years. There's a relation, of course, between it, and that's basically the transformation from research to technology. So when we want to transition all these cool quantum concepts from research to technology, can software be a solution? And if so, how do we need to build it? That has actually been a question in my head for a longer time. There are good examples, for example, NS3 that enabled quantum internet research. OpenAir interface acts as an open source reference solution for 3GPP. Unfortunately, Arun from Eurocom is not here today. But yeah, it's a very impressive tool. We have NetSquid to help engineers build the quantum internet, QNetSim to teach students the quantum internet. And at least from my perspective, none of those solutions was a good solution to solve the problem of working in heterogeneous teams on very complicated proposed systems. So the challenge is that everybody in those consortia that I'm typically in needs to collaborate, but everybody also has a different background. The PhD students should focus on the completion of their thesis rather than on the system design, or like on leaving a really nice completed system behind. It's hard to manage things centrally across a consortium. And yeah, we produce exceptional output, but the integration is hard. So we thought maybe we make some software with a simplistic common user interface. We try to cover essentials in experimental reality and in the experimental workflow, but also in theory. And here you see on the left-hand side already a small peek into what this system looks like. Those that think of LabVIEW, yeah, that's actually was it looks like LabVIEW. You are right. You can write your favorite black swan, or sorry, that's a white swan, new component, which is the crazy cool new thing you are working on. You can put all sorts of mathematics and theoretical physics in there, and then you can put this into a simulated network of other components, which might just reflect textbook knowledge, like beam splitters, lasers, yeah, almost. And in this software, we try to be rigorous in the sense that interfaces need to be defined. Yeah? So your new component should work well against existing interfaces, for example, in quantum optics. There are 2 publications about this. And one publication that I know of that is already using this system that we made, we collaborate a lot with Deutsche Telekom in the use of that software because they have a nice lab and they know the problem. We started a special issue, which is unfortunately closed already, and all the material that was submitted is under review. We also submitted one thing, and we are currently working to use the software ourselves to plan our own experiments. And here is a bit of a look at the user interface. So as you can see, it looks like LabVIEW. And it has a lot of possibility to add standard components, like here, this is optical fiber, but there are many other components in this particular experiment, which reflects a joint detection receiver and actually uses this one component that nobody knows how to build. That's the vacuum or not, non-destructive vacuum or not measurement. So that's a part of fundamental research that is put in there and which we hope to maybe work on with colleagues in physics, but all the rest can basically build already and explained also to other people based on this design. And if you are curious to learn more about the software, then today or right now is not the moment, but you can look into one repository where this example is in.
Thanks a lot, Janis. We have time for some little question. Does anyone in the audience have a question for Janis? Otherwise, I will just briefly ask you, Janis, thank you for your talk. So would you say that this software has also some, you mentioned for other softwares, but in this case, for education, for somehow building this gap between theory and lab experience for quantum physics, for example, or
we strive to build this bridge. So okay. Next semester we will actually spend trying to identify how to make a good course which uses that software. The special issue also required people to develop a Kraus operator representation of their submission, and they should also bring experimental results. So this was also another attempt we made to exactly cover that or build that bridge.
Okay, thanks a lot. So we thank again Janis